Hey kids, welcome. It's time for our last lesson of the exponential functions unit. So 4.5, solving exponential equations. The idea here is going to be pretty simple, and if we just stare at this box, this is basically going to explain the strategy today. So the big one that we're going to try to do is we're going to try and solve exponential equations. If we have a variable up at the exponent spot, we're really going to have a hard time getting that down. Later on, we'll figure out ways you can do it with logarithms, but for now, we're going to use this property that if we can get two sides of the equation having the same base c, then we can use the property that, I'm just going to zoom in here, if c to the power of x equals c to the power of y, then x equals y. So a really simple example of this would be to say 2 to the power of x equals 2 to the power of 3. Well, if they're both the same base, you really don't need to even worry about this. You could simply just say, well, x equals 3. Okay, so it's a pretty simple idea. It's going to play out a little trickier because quite often we're going to wind up having something like 2 to the power of x equals 4 to the power of 3. And now they're not the same base, but if you notice, we can often get them in the same base by replacing 4 with 2 squared. So we're going to look at some examples where we do that. If the bases are different, so the second point here, if the bases are different and they're not similar powers, then we're going to have to use what your textbook likes to call systematic trial, which is basically guessing and checking, or we'll use graphing technology, so like decimals or something like that. And then later on, we're going to use logarithms to help us solve this algebraically, but for now, we're going to take it sort of easy, and then we'll look at the more robust, complicated way of doing it with logarithms in the next unit. So example one's very simple here. Rewrite each pair so that they have the same base. So if we have 2 to the 3x and 4 to the x, the exponents are not so important. How do we get these into the same base? It's pretty simple. We could both express these as powers of 2. You could arguably express them both as powers of 4, but it's going to be much easier to get it down to the simple number. So this is going to get converted to nothing. And then this one is going to get converted to, well, 4 is 2 squared. So 4 to the power of x is the same thing as 2 squared to the power of x. And let's just take a second. Remember that the rule is when you're raising a power to an exponent, you multiply them together, okay? So this would turn into 2 to the 3x, and then this would turn into 2 to the 2x. Now they have the same base. For b, 8 to the power of x plus 1 and 16 to the power of x. Here you could, again, you could both write these as powers of 8. You could even write them both as powers of 16, but that's going to be tricky. The easiest thing to do is find like the common power to them. So it's sort of like a lowest common denominator in a way. This is going to turn best into 2 to the power something, because this can also turn into 2 to the power something. So 8 can be replaced with 2 cubed to the x plus 1, and this would be replaced with 2 to the power 4 to the x. This will end up being 2 to the power of 3x plus 3, and this one will end up as 2 to the power of 4x. So that's how we could get them looking the same. Okay, this next one here. So root 2 to the power of x, remember this can be expressed as 2 to the power of x over 2. That's what a square root can look like. Remember, square roots are square root of x is equal to x to the power of 1/2. So that's the property I'm using here. And I can also use the property that this can be expressed as 2 to the power of negative 1 to the power of x, because 1 over x is equal to x to the negative 1. So if I want these to look the same, then this is going to wind up turning into 2 to the power of negative x here, and then this is 2 to the x over 2 over there. So now they have the same base, and I could equate the exponents if I was solving that. Okay, this one here, similar situation. We've got 25 and 125, and you can probably look at this, and if you're getting the hang of this, you can determine that this is going to have to be expressed as 5 squared, and this would be expressed as 5 to the negative 3, because 125 is 5 cubed. So and then these would wind up being 5 to the negative 4 for the final simplification, and then this would wind up being 5 to the negative 3x. Okay, so in example 2 here, we're going to zoom out 1 sec so we can just do that. Okay, so we're going to solve for x by rewriting it the same way. So basically what we just did, what we just did is we just got a little practice rewriting them in the same base, and now we're actually going to solve the equations. So if you can do this, you should. Now sometimes you're just going to have to use the systematic trial where you're just basically going to be entering values in on a calculator, taking a guess at it. It's not really the best math, but it's the best math we can do for solving some of these questions. So if we're solving for x in this first example, I would start by rewriting the left side as 2 squared instead of 4 to the power of x, and the other side is going to become 2 cubed to the power of x minus 1. You can't ignore the bases quite yet. You have to use the exponent rules while we're in this form. So this is going to be 2 to the power of 2x, and then this is going to be 2 to the power of 3x minus 3. At this point, and only this point, you can now, we're using the property, if c to the x equals c to the y, then x equals y. If there was anything else, like a divided by 3, this property doesn't work. If there's a negative sign, this property doesn't work. So you have to have both of these two bases, here and here, absolutely identical with no other extra filler. Bases must be identical. Okay, but once you've got that, then the rest becomes pretty easy. Then we can just equate the two exponents. So 2x equals 3x minus 3. And then we solve this. We'll take 2x to the other side to get x. We'll take 3 to the other side to get x equals 3. If we want to verify this, we can do that. We can check our work here, and we can say, is it true that 4 to the power of 3 is equal to 8 to the power of 3 minus 1? Well, what's 4 cubed? 64. And then this is 8 to the power of 2, which is 64. Check so. Good. Okay, next one. So when you're looking at something like this, you've got 8s and 4s and 2s. So the common base here is going to be 2. And there's not really a method I'm using to figure that out. I'm just sort of common sensing it here. Okay, so this one over here is going to be a little tricky. I'm going to break this up. So 4 is 2 squared, and then the cube root of 2 is actually 2 to the power of 1/3. So once we have this, now we've got to remember that, let's see, I can simplify the left side, so that's 2 to the 3x plus 3. When we're multiplying powers, we add the exponent. So this is actually going to be 2 to the power of, somewhere off on this side, you have to add fractions. Okay, so this is actually 2 to the power of 7 over 3. Now that the bases are identical, we can drop down the exponents and ignore the bases, and then we can solve this. So the way we're going to solve this, we're going to have 3x equals 7 over 3 minus 3, and that's going to take us over here. So 3x equals negative, 2 over 3. So x would be equal to negative 2 over 9. Checking this one's a little harder, but you could go ahead and do it. You could put it in there. But for now, I think we'll just trust that this one works. Okay, for C. 5 to the 4x minus 3 equals 2. Now, is there any kind of base I can express 5 as so it's going to be the same as 2? And really, there isn't. So what we're going to say is there's no common base here. So the best way we could solve this is we could either graph this and find it on Desmos, but if we don't have Desmos handy, we're going to use that idea of systematic trial. So basically guess and check. So we're going to go, what value of x is going to work here, and we're simply going to try some out. So 5 to the power of 4. So this is where you're just maybe going to take a stab in the dark. Okay, 4 times 1. So we're going to just try x equals 1. This is not very efficient, and this is definitely not my favorite way to do math, but it's worth looking at. So 5 to the power 4 minus 3 is 5 to the power of 1, that's equal to 5? Okay, so that's too big. So now we could maybe try, x equals 0. So we could say 5 to the power of 4 times 0 minus 3, and that's equal to, oh shoot, that's gone, so that's like 5 to the negative 3. So that's 1 over 5 cubed, that's 1 over 125, that's too small. Okay, so we kind of have a Goldilocks situation here. So now you're maybe going to try x equals 0.5. So then you're going to go, okay, well 5, 4.5 minus 3, what's that equal to? And you're going to go, let's see, that's 5 to the power of 2 minus, so that's 5 to the power of negative 1. That's 1 over 5, so that's 0.2. Okay, and then we're getting a little closer, so it's going to have to be a little bit more. So that's still too small. That's just too small. So then we're going to try maybe one last one. X is equal to 0.7. And I'm just kind of making up these numbers because I feel like it might get us close to where we're trying to be. So this is now 5 to the 2.8 minus 3, so that's negative 0.2. Okay, and at this point now, okay, I'm not totally sure what the answer is, so maybe we jump over to something like Desmos and we write 5 to the power of negative 0.2. Okay, we got 0.72. All right, so you might even sit here and fiddle around with it. Maybe 0.1. Okay, anyway, so it's not actually super crucial that we get this just right. And you can just sit here and play around with some numbers until, okay, well, anyways. So it seems like probably our best, although now I've forgotten what that number actually was, our best bet is to pick a number. Let's see, so I tried 0.7, no, 0.2, my apologies. So we got 0.7, okay. Anyway, so we can sit there and we can fiddle around with it and wind up getting the best answer. Now, this is not a very efficient way of doing things. It's incredibly inefficient, actually. So what I would suggest is if you are going to give this a go here, I would consider maybe just doing it graphically. So if we want, we could actually go 5 to the 4x minus 3, and then we're going to set this equal to the line y is equal to 2. So what we can see there, okay, so we can see they actually do cross over each other, and there is a solution. And if x is 0.25, we would have got something more useful. And in fact, if I actually would have been smart, and I think I might have actually been trying the wrong numbers, but if we tried x is 0.25, we should wind up seeing here that this, let's see, that would be, oh, I screwed up. Desmos really likes when you put your brackets around the exponent. Okay, let's try it one more time. Sorry, my apologies. Okay, so there we go. That's better. 5 to the power of 4x minus 2. Make sure you put your brackets around. Make sure you're looking at it. I felt this didn't seem right. Okay, so 0.858. All right, so we're just going to scratch that because I was thinking there's no way that's going to work. 0.858. Anyway, you get the point here. This isn't really super worth me calculating, but if we would have wound up spending enough time sticking with it, we would have got about equal to 2. Okay, so anyway, that's not the main emphasis, but just be aware that if you're asked to do systematic trial or graphing technology, well, it works. Okay, let's go to D now. I picked this one here because we had something sticking out in front, and you got to make sure when you're doing this, you got to deal with that guy. So the way to deal with this is to go, 9 obviously is 3 squared, and make sure you're thinking about this in terms of multiplying powers. So this actually becomes 3x squared, and you have to combine these. Don't you dare start crossing them all out like that. That is actually not something. You've got to get it into one single power. So this is going to be 3 to the 2 minus x. And at this point, okay, well, look at that. So this is PayPal. I haven't used PayPal for 20 years, so I don't know why I'm getting that. So we get x squared equals to 2 minus x. And this is going to wind up giving us x squared plus x minus 2 is equal to 0. This is a good old quadratic equation, so we're going to solve this. Factoring will be useful here, so we'll go x plus 2, x minus 1. What this tells me is that I get two possible answers for x. If I really want to check this here, x is equal to negative 2 and x is equal to 1, I could go and I could graph it. I don't think I'm going to, well, I could actually enter it. Yeah, you know what? Let's do it algebraically. I was thinking this is going to be hard, but it's not going to be that hard. Just because we get two answers when you're doing quadratics, it's pretty handy to verify because sometimes you get extraneous roots, but I don't think that's going to be happening too often here. Okay, so is this true? Is it true that 3 to the power 4 is equal to 9 times 3 squared, which is 9? So this is 81 equals 81, checks out, and we could even check the other answer here. So this would be 3 to the power of 1 squared. Is that equal to this? So that's 3. This is 9 times 1 over 3. 3 equals 3. Yeah, that checks out too. Okay, so they're both good answers, but it might be worth your while to verify. Okay, the last one here. This is probably the most challenging one. You can give it a try if you haven't tried any of them already, but let's have a look here. So the common base is going to be 3, so this is going to get turned into, so 9 gets converted to 3 squared. That's to the power of 2x minus 1. And then 1 over 27 will be 3 to the power of negative 3, x plus 2. Okay, so this is going to become 3 to the power of 4x minus 2, because you multiply the exponents. This will become 3 to the power of 3x minus 6. And then we can finally turn this down into, get rid of the bases, and just evaluate the exponents equal to each other. So we'll move all of the x's to this side, 7x over here. We'll take 2 to the other side, and we'll get equals 4. And we'll get x equals negative 4 over 7. Super keen to verify that one, so maybe I won't, but it can be done. Desmos can also confirm it. So if we really wanted, we could jump up there and we could go 9 to the power of 2x minus 1. And then we could equate it to 1 over 27 to the x minus 2. So this would be, in brackets, 1 over 27 to the power of, and we want to use brackets for the exponents, x minus 2, no, x plus 2. All right, so what we should see here is we get an answer, which is only one crossover point, so negative 0.57. I got negative 4 over 7. Let's just confirm. I think that's right, though. Yeah, 4 over 7 is 0.57. Okay, perfect. Moving on. Okay, the last part of this is the application. So there's actually a ton of applications here. This general equation is going to be super helpful. So just take a second, stare at this. This equation here is going to model any kind of growth and decay where it's exponential. So what this equation looks like is A is just for amount. This could be any letter, but just A is fine. A naught is the initial amount. This was mentioned before. C is a growth factor. So that's the relationship of like whether it's getting multiplied by 2, divided in half, interest rate of 5%, whatever. Little t is time goes on top, and big T is the time for growth to occur. So that might be like the time it takes to get your interest on a bank account, or the time it takes for a nuclear isotope to decay. So that could be the half-life time. So this is a general structure here. You don't have to memorize a bunch of different formulas if you just understand this one basic thing. Now, the way this is going to look is going to be totally different, but if you notice, there's a lot of similarities between all of these examples. So the basic equation does get modified on whatever the application is, but just check out these sample equations and just see how they're similar. If you have a population of bacteria that doubles every p hours, well, we're using p for population, and then we're saying the initial population, you multiply by 2, that's the doubling, and then it happens every 6 hours. So in this case, the 6 is on the bottom because when the time is 6, you want the exponent to be 1. So you get a single doubling. And when it's 12, you want 12 over 6 to be 2, so you get 2 doublings. Mass of a nuclear isotope is similar. The growth factor here is 1/2 because it decays by half. That's why it's called half-life, and of course the half-life would go on the bottom because it happens once every that many years. Money, if you saw the Something Interesting video, which you definitely should have, if you did not, go back and watch it, we derived an equation that looks something like this. This is your interest rate. The interest rate gets divided by 12 because you're getting 12 times a year. And then in this case, the exponent is 12 times t. So this is not actually any different than t over capital T, but capital T, which is the time it takes to get your interest paid out, is 1/12 of a year. So instead of going t over 1/12, it's much easier to just say 12 times t. That looks like a 72. That's not supposed to be. Finally, here's another one. I've seen a question like this in a textbook somewhere. Intensity of light passing through water loses 4% intensity every meter depth. The 0.96. It's usually easier to say this is what's remaining. You can't go like this. 0.04. It just doesn't work out. Okay. So here's an example. A 320-gram sample of radioactive uranium has a half-life of 20 minutes. Okay, so write an equation to model the remaining mass after t minutes. So we're going to say m as a function of time is equal to the original amount, so it's 320. You don't have to put grams. It's half-life, so you're going to have 1/2 of it remaining, and then after 20 minutes, it's going to be gone. So it's going to be half of it's going to be gone. So it's going to be t over 20. And that's as simple as the process can get. So that's your initial amount. That's what you would call m naught. And then the rest is everything that was just explained. Okay, for B, how long does it take the sample to decay to 2.5 grams? Well, in this case, this is saying the mass is 2.5 grams at what? T, okay? So with our equation here, we're going to replace this with 2.5. We're going to write 320. We're going to go 1/2. We're going to go t over 20. Okay, so now we need to solve this. The easiest way of solving this is to try and see if you can put this all into powers of a half. So what I would recommend here is to divide 320 to the other side. So you'll get 2.5 over 320 equals 1/2 t to the power of 20. And then see if you can simplify this fraction, because this does not look like a power of 2, but I bet you we can make it kind of look like it. So can you divide the top and bottom by 2.5? If you can do that, that's going to be pretty handy. So I'm going to try and divide the top and bottom by 2.5. Okay, that's going to make this equal to 1. What's 320 divided by 2.5? I think what I'd prefer to do is I'd actually prefer to do it this way. Then I'm going to multiply top and bottom by 4. By the way, this is just my thought process in doing this. This is not the way you have to do this. You could probably use a calculator if you want, but when I'm thinking about dividing by 2.5, I like to do it this way. I like to think of dividing it by 10. Okay, so this turns out this is actually going to be 1 over 128. All right, so we got this simplified down into 1 over 128 equals 1/2 to the t over 20. Okay, so 1 over 128, that is actually a power of 2. So this is 1 over 2 to the power of, and this is where you can actually pull out your figures and go, okay, so you go 2, 4, 8, 16, 32, 64, 120. So that's to the power of 7. So that's 1/2 there. And once we get it here, you can now ditch the bases and you can say t over 20, or you can say t equals 140 minutes. Now there's a pretty good chance you could have just sat there and you could have just done it this way, right? Okay, 320, that's times equal to 0. You could set 160 is times equal to 20 minutes. You could have cut that in half. And you can keep doing it this way too, right? Like, it's not like common sense stops working. So that would be 40 minutes, 60 minutes, 80 minutes, 100 minutes, 120, this would be 140. You can totally work it out. But the process I just showed you can be a lot more useful when you're actually trying to solve things that are much harder to list out, or we're looking for more specific values. Okay, last question. If $5,000 is invested with a 5% annual interest rate compounded quarterly, determine how long it would take for the investment to double. So let's start by writing the amount. The amount as a function of time equals a naught. The general equation is 1 plus I over n times nt. This was discussed in the Something Interesting video. So if we have $5,000 invested initially, so that's going there. And we want it to double, so we can write in 10,000. Similarly, we could have wrote A and 2A, but whatever, we got the numbers down. A 5% interest rate is going to be 0.05. It's going to be compounded quarterly. So what that means is we're cutting the years into quarters. So n equals 4. And then this is 4t. Okay, so the first thing you would have to do is you got to get rid of these coefficients first. So we're going to divide both sides by 500. These are going to be gone. We're going to have 2 is equal to, and now I'm going to actually work this out. 1 plus, okay, 0.05 divided by 4. That's 0.0125. Okay, I got a bad feeling about this. So that's 1.0125 to the power of 4t. Okay, there's no way I'm going to express these both in the same base. The numbers just don't work out. So what I can do here is I can do a little bit of guessing and checking if I like, or I can use some Desmos. I don't really want to sit here and show you all the guessing and checking. That's not really hard. You could say, okay, well, let's try t is equal to 10, and then you could work it out. Is this the same thing as this? And, you know, this would be 1 to the power of 40, and we could work it out. But let's just go ahead and get an answer here using Desmos. It's probably more appropriate in this case. Okay, so the way we would enter this, we go 1.0125. So we go to Desmos. We go 1.0125, and you have to raise it to the power of, and it's going to be 4x. Don't do t, actually do x. And I want to set that equal to the other side, y is equal to 2, over here. You can't just enter 2, you have to write y is equal to 2, and you can't put it all on one line either. So a separate line, y is equal to 2. Okay, then we zoom out. Maybe I'll click the home button here because it'll give me a better zoom. Okay, so what we can see is right here, I get a value of x, 13.949. So what that tells me, and I'll go back to the idea of t, it's 13.949. Okay, so that's really darn close. I'm going to just approximate that to be about 14. So in this case, you just got to take a little second think. What is the units here? In the original question, we're told annual interest rates. So this t, the t is in years. T in years here. If we put it in months, we'd have to modify the equation a little bit. So this is 14 years, which translates to 14 times 12. Okay, well, we should be able to do this, but it's hard when you're doing a video. I know 12 times 12 is 144, so I'm going to add 24 to that, so that's 168. Okay, so this should be about 168 months. There's a little fraction of a year missing, so maybe it's a little less. Maybe it's 167. That's not super important or super interesting here, but we can see it's going to take about that many months. If we're really upset about this, we can go 13.949 times 12, and I guess we would have got 167. Okay, close enough. So you know what we're going to do? We're just going to go approximately. Okay, anyway, that is the lesson. The moral of the story here is, as much as possible, if you can write exponents in the same base, you should try and do that. When that fails, though, you can jump over to trial and error or use Desmos or something like that. All right, thank you for watching. See you on the next one.